So, blowing off steam with the team, skiing, racing.
Well, one of the ways we blew off steam a little bit was in fact, the guy that was the Microsoft guy that had joined us early on decided that it would be a great idea to go down to Laguna Seca and go to the Russell Racing School. So I think maybe about 8 of us went down to the school, and we went to the beginner school, which I think was 4 days, and we were in a Mazda open wheel car, and that was a good thing to blow off a little steam, and it was really an eye opener for me about driving a race car. I really wasn't very good at it, or wasn't as good as I thought I should have been at it. And the beginner school, they just teach you basically how to drive the car, about the dynamics of the car, G-forces, cornering, and all that sort of stuff. But then they have an advanced course where you actually, at the end of the course, you get to do a race. So a few of us decided, well, we'd like to go to that too. So I don't know, a couple 3 months expire, and we go down and we do that. And so we do the race. We go through the advanced school, and they do some more things. And I'm getting a little better at it. And we finish that. We do our race, and that was fun. So I thought, well, maybe they have the school series, what they call a school series. And you basically go down once a month, and you race on Saturday and then on Sunday, and you come home. So, and Debbie was involved in this too. Debbie came down and did the beginner one, and she did the advanced one. And so she and I would go down there every month for, I think we went down from, somewhere in March to September, something like that, every month. So it was 10 races or something like that. So I did that, and that was fun. And so then they had every year they had what they called a pro race. In the pro race, they didn't have governors on the systems, but they sort of would they would open them up a little bit. They reprogram the ECU, the engine control unit, and give them a little more horsepower. And they say we're going to have a pro race now, and the pro race meant there was a prize package, and you could win some money. I think probably the top was $10K or something like that. But this would draw a lot of drivers that were pretty good. So I did one of those. I think I finished next to last only because one guy, my first one, only because the other guy was worse than I was. So then I got involved with a guy that was one of the instructors down there, and another guy that owned a race team, to import an Atlantic car from New Zealand. And that was when I started into racing really seriously. And so I owned that car, and he raced that car one year, which was 1995. And the next year, I decided that, well, we really should have a new car to race. So I bought a new car, and so the question became what to do with the old car. So I climbed in the old car, and geez, I was pretty good. So I decided, well, I'll race in this series. So I started racing the Atlantic Series, and I raced 56 races in that series. Wow. It had some pretty horrific accidents. Nothing that I was really hurt really badly in, but one at Laguna Seca is sort of an infamous one because ESPN played this over and over and over again for 5 minutes of broadcast time or something. And it was in one of the turns I did a longitudinal flip. So you think about a flip as going end over end. It wasn't end over end, it was a barrel roll flip. I did a flip like this and landed on the top. And it was in a corner where there was really dusty, and the dust flew, and there was big dust clouds. And
what turn was that?
It was turn 10 at Laguna Seca.
A fast downhill sweeper
to the right.
To the right, yeah.
And ESPN picked that up, and they just played that. They played it over and over because there's a certain amount of time the yellow goes out, they have to clear the track, then they have to, get the wreckers out and upright the car. So the race is, stopped. But they just keep playing this over and over and over again. So that was sort of my big wreck. My best result, I finished 8th one time at the Milwaukee Mile. This particular series, we raced Monterrey, Mexico, which was a real eye-opener. The racetracks here are pretty safe. Yeah. The racetrack there was not real safe. I raced in Homestead, raced in Cleveland at the airport, Mid-Ohio, which is outside of Columbus, Montreal, Trois-Rivières, which is up by Quebec City, Vancouver, British Columbia, Portland, Long Beach.
Road America?
Road America. Road America. Road America. This is Elkhart, Wisconsin. Yeah, I had a big wreck. Well, that's my second biggest wreck, or maybe my first biggest wreck was at Road America. There's a turn there they call the Kink, which is about 140 or 150 mile turn, and I lost control of the car and hit a stone wall there, and
ouch.
I got out of the car, and the car was rocking like this, and I couldn't really understand why that was the case. And I looked down, and all 4 wheels are gone. I'm just sitting there in the car. The car is built with what they call a monocoque tub, and I'm in the tub, and the engine's still on the back, but none of the wheels they're all gone. So I did race at Road America.
Yeah. Your favorite one?
The Milwaukee Mile, by far.
Yeah.
Yeah. Oh, Nazareth, Pennsylvania. We raced there too.
Any analogies from racing into software development?
Yeah, actually, I think there is, and it's focus. I've always been a person that really can focus on the job at hand, and driving a race car is focus. I mean, what happened 10 milliseconds ago, it's gone. You're going to focus on what's coming up and what's going to happen. So I think there's some analogy there about being really successful. I mean, in anything is to focus on what's important and what you have to achieve to get to the success of. So in race car driving it was just another example of that.
So the super intensity of concentration.
Yeah, it's like
when you're writing code, how do you achieve that? Can you stand music being on, or want to be in a quiet office, or?
In general, noise doesn't bother me much. I would prefer that somebody's not. There's one guy at work now that whistles, and that that's not a problem. But he whistles down the hall, and I'm like, I really don't like that. But generally, noise doesn't bother me much. But I do focus on what's going on, especially if I write a new piece of code. I write the code, and I will spend maybe 3 or 4 iterations of executing the code in my mind, all the air paths, all the paths it can go through, to see if I can prove that it's correct before I even run the code. And most of the time when I run code, it pretty much runs the first time. It may not be absolutely correct, but it will run, it won't crash. So that's being able to focus on what's going on and not have things bother you or whatever.
In the NT program, it was demolishing bugs, and how would you change the process to create less errors and make them easier to fix?
Probably the easiest bugs to the question is how to make bugs easier to fix and
fewer of them.
Pardon?
And fewer of them.
Fewer of them. I think fewer of them is probably the easier of the two, because the fewer the bugs are, the harder the ones that are left are going to be to solve. And the hardest bugs to solve are ones around synchronization. They're not around correctness of code flow. They're around the correctness of synchronization, where there's not the correct barriers, there's not the correct locks, or there's race conditions between code paths or something. One of the things that also exacerbated the 5 years was multiprocessing. I had the bee in my bonnet when I went to Microsoft that we were going to produce MP systems. And nobody else was producing MP systems. DEC had, at that time, they had the 782, which was this funny asymmetric thing. And we had 1170 that actually was SMP, but there was some Unibus problem that we decided not to manufacture that. So SMP problems, synchronization is a big problem. The problem with less bugs is, I think, through the engineering process itself and the people. You've got to have, quality has to start from the bottom up. It can't start from the top down. You can't legislate quality. Quality has to be something that's inborn in everybody at the lowest level. And any link in the lowest level that doesn't produce a quality piece produces bugs up the line because they interact with other pieces of the system. If you're building the lower levels of the system, then your leverage as far as causing problems up in the levels is very high. So I think reducing the number of bugs is basically thinking more about quality and paying more attention to quality. I don't think that necessarily you have this thing, well, we'll do 100% test afterward. You know, we'll do everything and then we'll test to see how good it is. It's got to be built in to start with. So I think building systems with fewer bugs means paying attention to that all the way along. And not, for me, I hate it when there's a bug filed against me. I don't like that at all. And I don't want that bug to exist filed against me for any longer than I have to. I'll drop everything to go fix that bug because I know I can fix that. So there needs to be that kind of mentality. I mean, there's a lot of people that say, oh yeah, I got 50 bugs, so, you know, I'll get them fixed. Well, it's like quitting smoking. You know when the best time to quit smoking is? Right now. It's not an hour from now, or a day from now, or a week from now. It's right now. So the best time to fix the bug is right now. So that would be fewer bugs. Make them easier to fix. I don't know how we make them easier to fix other than the building better tools for analyzing what's going on, I guess, is primarily the way we would make them easier to fix. And we have lots of tools now. We have lots of tools that do the same thing that, you know, somebody has said, well, that's a good tool, but I'd like the tool to do this. I don't own the tool, but I think I could build a tool that was a little better that would do this, and maybe we could find something a little better. And so we have a lot of tools. We have a lot of source level tools. One of the big problems that we had partway through the evolution of NT was hitting a big security attack or wall or whatever somewhere after about 2001, somewhere in there. You know, the internet, we really got going on the internet somewhere in the late 90s. And the internet suddenly had problems with people with viruses and trying to attack your system. So we developed some tools that analyze the source and try to find places where you have buffer overflows are the biggest one. And the amount of buffer overflows that we had was just mind-boggling. And it was like we have this tool, and the tool says, look at right here, this could overflow. And so that was great. I mean, that made it so that it lowered the bugs. Even things like arithmetic overflow can cause a bug because maybe you're calculating the size of the buffer that you want to allocate because you got a byte count. and you do this computation, and geez, that overflows. And now it looks like you need a small size. So you allocate that size, and then you use this other size to transfer data into it, and all of a sudden you have a problem there. So we have some tools that analyze the source and actually point out places where there's bugs, and we actually fix those like they're bugs. The problem with those tools are that they're static analysis tools, and they have a lot of false positives. So you see a lot of things that aren't really problems, and it can't see some things. You know, you may have, in your code, you may have had logic that made it impossible for the thing that it's complaining about to occur, and it'll say, hey, this is bad. So those have to be filtered out, and so we have ways to filter that out too.
If you go back a little bit to getting programmers to really produce good code, is there a Dave Cutler school of how to get a programmer moving along in that direction?
Do I have a way to move people to build good code? I guess the only way that I can say that I have helped people build good code is by example. You know, everything that I do, I try to make it my best, and everybody sees the source, and obviously they see that I don't have a very big bug count or a 0 bug count. They look at my code, and I hope that really helps them become better programmers. But another aspect of this is really, with the young people starting out, to really ingrain in them the importance of quality. I mean, for me, there's nothing worse than software that doesn't work. I mean, I just can get really upset with software that doesn't work, where it's obvious that something something simple. I mean, if something doesn't work on your phone, or it doesn't work on your tablet, or it doesn't work on your PC, that should work, it should infuriate you, because it just should not be that way, right? Mm-hmm. It should be, all the stuff that doesn't work should be stuff that is little tiny things. Maybe it's like there's a few pixels over here that are wrong, or something that's just minor. In fact, a lot of the bugs that have been and continue to be filed against NT are these kind of things. They're cosmetic things, and they have low priority. So those things are not upsetting, but it's upsetting when you have something where you ship a product and it's in the field for 4 months, and all of a sudden there's this disaster that happens where you wipe out, somebody's data. And then all of a sudden it's like, wow, that's really a problem. So I think quality is something that, starting out with young people and saying, hey, we really got to have quality.
So you come to 93, I think it is, and the final...
93 is
the release date of NT, the official release, millions of copies shipped.
The initial version of NT is shipped in 1993. And then we shipped NT 3.5, which was alpha support, about 6 months later. And part of that was also a kind of cleanup, let's improve the performance of the system release. We did not have the performance level in the system in the first release we would like to have. It was a little bit bloated. Now, bloated in those days was like, maybe it took 24 megabytes as opposed to 2 gigabytes or 4 gigabytes. So Daytona was kind of this dual thing where it was called Daytona. It was actually the Daytona release, and our big thing there was the racetrack and everything. And I think we actually may have, we had some racetrack stuff because we'd been all off to the race school. And we incorporated alpha support, and then just a little bit later than that, we did the Power PC. So that brought us to the end of the first release, and then the next release was NT 4.0. And NT 4.0 is an interesting release because at the end of the release 1, we actually call it 3.1 because Windows was 3.1. The 16-bit Windows was 3.1, and the feeling was that nobody would buy an operating system that was a 1.0. Mm-hmm. Nobody. So it would start out with a number that wasn't a 1.0, and we'd pick the same number as the 16-bit thing. So then we had 3.5 and 3.5.1, and the next one was going to be 4.0. And in the meantime, another guy had been hired from Banyan. His name was Jim Alchin, and he had actually was starting another project called Cairo. And Cairo was envisioned to be a system that would incorporate some of the things you now see with internet search, only it would be locally. An indexing file, a new file system that had indexing all your mail and everything. And it was internally in Microsoft, it was called Information at Your Fingertips. And he started this project, and it was kind of running in parallel with the tail end of release 1. So when we started release 2, actually it was NT4.0. The Cairo project, Alchin actually became my boss, and the Cairo project became part of the NT development, and that was supposedly where we were going to be going. And I was really worried about this, so I proposed another project we called it Tukwila. And the reason we picked Tukwila was because we know where Tukwila is and we know how to get there. It's just down the street. So I convinced Jim that we had the capability to do both of these at once and throw one away. And it turned out that the one we threw away was Cairo. And NT4.0 was probably one of the best systems that we produced, certainly not functionally, but as far as its acceptance and quality and performance, and it contained it was in 1996, so it was just after Windows 95. We'll talk a little about that lineage of system.
Yeah.
So it contained the new graphical user interface, which was drastically different from 3.1. 3.1 was it was graphical, but you sort of put things together. You built your menus, and you had to do a whole bunch of stuff. And then the new UI actually had all that stuff. Everything when you got the system was already installed with start menus and all that stuff. So NT4.0 had the new UI in it, and it was an evolution of NT. Cairo would have been an evolution of NT also, but it would have had a new file system, a new shell, just a whole bunch of new mail system, everything. So I started to divert I digressed into Windows 95, and why Windows 95 came about. Windows 95 is actually built on a DOS code base. So it's actually the 16-bit system with the capability to run 32-bit programs. And it included this new UI. And it actually was very popular and sold a lot of systems. It sold, in that time frame, it sold a lot more systems than NT sold. But NT sold in the places where you were doing enterprise stuff. You needed some security. You needed to run you wanted to run file servers or print servers. Those are the only kind of servers we had then. So NT was alive and well and very healthy, but at the same time, Windows 95 made the company a lot of money. And then they continued on with that same code base for Windows 98, and then was with Millennium, which I believe was in 2000. So, and it died. It completely died. It was a non-extensible, it was bug-ridden. It was notorious for just hanging, it just freeze. And that was not unexpected because it was built on DOS. It wasn't built on...
And terrible security.
No security. None. One of the things, you didn't ask me about this, but I might say something about security. We started out in the beginning to have really robust security, and we designed the original security model was pretty robust, but by today's standards, completely different, because in those days, you were protecting things you were protecting people against file access and system resource access, but it wasn't like the security today where somebody invites the breach right into the system. They're in the browser and they click on something and here comes a program they didn't even know about. All of a sudden it exploits a buffer overflow and bang, it puts something in the operating system and now you're under the control of the virus, right? So anyway, there was a lot of controversy about whether we should make people log on or not, because the original PC, you turn it on, there it is. Well, Bill didn't, we're talking about security and the fact that we maybe shortcut the system a little bit with security in the beginning because the PC mentality was you just turn on the system and use it, and we had come from the background of time-sharing systems where everybody logged on and everything was shared, and you were worried about people accessing your files, and geez, if it's a PC, you own it, you can access your files. So we actually designed the security system and built the security system, and we did have logon, but there were some aspects of the system that we didn't do quite as well as we could have. One was when you install an application, you should really install an application for the user that installed it, not for the system. But since it's a PC, you install it for the system. So that was one problem, because now you assume now that everybody is going to use this thing, and that if two people have two different versions, well, that you can't have that. You can only have one version. And then the other thing that happened with that was we would have all these people that were reshipping binaries. And so somebody would have an application like Office, and they'd reship a binary, and somebody have maybe a database application that would ship a binary, same binary. Never been tested against the other guy's product, right? So and we're still somewhat trying to work through this about state separation, which is part of casting this as part of security, is separating everybody's state so it's only their state. Mm-hmm. So, but NT does have security and had security built in, whereas Windows 95 did not.
So the end of the DOS Windows comes to, it can't go any further. And where does NT go in terms of influencing the future, let's call them personal operating systems?
Where does it, you mean like the
XP, 7,
so on. Well, let me tell you, it's all NT. There is nothing that's not NT. Win 10 is NT. It's all the same stuff. It's an evolution of the same code base going all the way back to 1988. There is some interesting divergent along the way. If you want to go into that right now, or
yeah.
It's sort of a little bit later, because I was going to start.
Well, take the direction you want to take.
Okay, I was going to say what happens after NT 4.0.
Yeah, good.
After NT 4.0, NT has grown to 400 people, and I'm sort of at the point of maybe I don't want to manage 400 people. Maybe I want to just work on the technical things that are important. So I decide at NT 4.0 that I'm not managing the system anymore, that somebody else is going to manage the system, and I become an individual contributor. And being an individual contributor from then on basically meant I was doing the same things I was doing on the coding implementation side as I was doing before. I just wasn't carrying all the other stuff with me. So the next system we produced was Win2K, Windows 2000. And Windows 2000 was probably one of the first systems that we really produced. We produced a separate server system, server SKU, from a personal SKU. I don't know whether we produced the server SKU. We probably produced the server SKU for NT 4.0 too, but the 2000 was more oriented towards that, about writing server applications. Win2K was another, great system as far as the reliability and everything. And my part was just basically any new features we put in the kernel, performance, nothing real big. And then we shipped that in 2000, and in 2000, there's a guy that's in charge of the consumer group, and there's a guy that's in charge of the server group, and they've been working together under another guy to produce the system. But the guy that's in charge of the consumer group decides that consumers don't need the quality that the server group needs, and that the server group's laundry list of features that they want to put in the next release is way beyond what they need for the next consumer release, so we split the code base. We split it in XP, and the other one was the server 2003 code base. And that turned out to be not a good decision. And what happened there was the server 2003 code base, we fixed all the security problems we were having. We put in the server features, and it actually turned out in the end it almost shipped at the same time as the XP code base. And the XP code base shipped with some new UI stuff. It had this the new start button and some other stuff. It was mostly UI work, but also shipped with a lot of security problems and more bugs than the server 2003. So, and I worked mainly on our server 2003, and about this time, I don't remember the exact date, but it was slightly after 2000. AMD came to us and said, we have we have an extension to the x86 architecture that will extend it compatibly to 64 bits. Are you interested? And one of the things I kind of left out here is the addition of yet another platform which was in 2K, which was the Itanium. We added Itanium support in Win2K, and the Itanium would run x86 binaries, 32-bit binaries, but it wouldn't run them at speed. So there was a speed penalty. Plus the fact that the Itanium was never, ever as fast as the fastest x86, ever. So AMD proposing this extension, looked kind of good. And so we sort of looked at it and said, well, it looks pretty interesting. Why don't you go back and come back when you've got it more solid and you think you really want to build it. So they come back in like 6 months and say, here it is. And I look at it and say, boy, this is great. The x86 runs at speed. We can produce a small, like the AME thing, we can produce a small wrapper envelope that just executes x86 binaries, and they'll run at whatever the speed of the processor is. The 64-bit stuff will run at the speed of the processor, except it'll have a bigger address space. So I said, this is pretty good. We need to talk about whether we're going to do this or not. So I don't know, not very much time went by, and there was not much happening. And I went to Ulch and said, we're doing it. We're just going to do this. I'm going to do it. I got a couple guys, and we'll do it. So basically 4 of us started out to do this, and we had done a lot of groundwork on making our code base data type neutral as far as pointer size because of the Itanium, and also because we were actually at one time doing a 64-bit alpha system, and then Compaq said, we're not building those anymore, so we quit doing that. So we started out on what became the x64 version of NT in the early 2000s. At the same time, AMD was developing the architecture and got a pretty good say in some things that were really important. I think we got about 6 features put into the processor architecture that I consider to be, one of them was absolutely essential, and that was they put in relative addressing. And it's 32-bit displacement. So it meant that if we were willing to, if we were willing to say our binaries were never any bigger than 2 gigabytes, then that displacement would always span a binary. So they put in the relative addressing, they put in some other things that were performance oriented, and I had a really good relationship with the lead microcode guy. I mean, Kevin McGrath was just great. And we, going back to this, how important this 32-bit displacement thing was, maybe you wouldn't think that would be important, but one is position independent code. It's hard to write code for the 64-bit architecture that isn't position independent, which means that one of the main security things that you do is something called ALSR, which is address space relocation randomization. So you take an image and you randomize where you put it in the address space. Well, you have to relocate it when you do that. Well, if there's no relocations, you don't have to do much, right? Now, there still can be relocations, but to have position-independent code, you need the code to be independent as opposed to the data. I mean, you can always produce pointers to the code or the data. So anyway, we decided to do that with a Windows 2003 code base. In the meantime, the XP is shipped, and we're producing a system on the consumer side called Longhorn. And it became, I called it Does It Matter Horn, because it became so bug-ridden and so hard to actually get it to run that eventually it got to the point that I convinced Alchin, I said we should just junk that code base and start over with the Windows 2003 code base as the new code base. And we did that. We started over. That system became Vista. And Vista was, that's the way that got delivered was Vista. But we actually delivered the x64 support as a service pack to the Windows 2003 server. It was Windows 2003 Server SP1, and it had some new SKUs, and they were 64-bit SKUs. There was a professional desktop SKU, and then there was a server SKU. And that turned out to be very successful. I mean, everything's 64 bits now, almost everything. The telephone's not, well, I can't say the telephone's not 64 bits because...
Your cell phone is anyway.
Well, the cell phone, it turns out, the cell phone turns out is actually going to 64-bit ARM. So they want more than 4 gigabytes of physical address space. So they're going to go to 64-bit ARM. There is some places where I thought the 32 bits would entirely go away, but there are some things like cell phones where smaller pointer sizes actually do end up meaning less memory. You need less memory, and on phones, less memory means less power drain. Less power drain means happier users. Okay, so in the meantime here, we shipped 2003, but just before we ship 2003, we have to go back to XP again. And we have to spend a ginormous effort on XP to bring it up to all the security enhancements we've made to the server system. So basically, we do XP Service Pack 2, which is basically a re-release of that software. So that sort of brings us to the point where, and again, this is all NT. This is not, you read Mary Jo Foley. I don't know if you know who she is. She's written about Microsoft forever, and it's like, this is a new operating system. Well, it's not a new operating system. It's an evolution. It's like every time Linux comes out with a new release, it's not a new system. It's an evolution of the old system. So the XP SP2 was really a new system because it was a re-release of almost every single binary. And then we went back to, we did XP, we Service Pack 2, then we did the x64 release, and then we went back and put the resources back on Vista. And so Vista came out basically as a 64-bit system and 32. And of course, Vista actually supported, I think Vista actually supported the Itanium also. Meantime, one of the things we left out here is the RISC systems were dropping off. And the reason, here's why I think they dropped off. I think the RISC guys were so focused on simple architecture with simple implementation that Intel was like, they got this architecture, it's a little complex, but they got lots of transistors. They got lots of design and they got lots of verification expertise. Let's put these transistors to work to make everything run faster. And running faster is things like very sophisticated branch prediction, better caching, set associative caching, and just all sorts of stuff. Speculation, all that the RISC guys are like, well, we don't really want to do that stuff. We want this to be simple. So the thing about RISC having a performance advantage just kind of went away. It went away because they didn't want to, there was nobody that had the resources to put to work on the chip architecture and the chip design that Intel did, and they didn't have the resources to do the big designs with all the transistors they had. I mean, they're billion transistor chips now, right? So, and the RISC guys are going to, they want to build, say, hey, look at this, we built this machine with 300,000 gates, right? Like, so what? Right. And this stuff on the Intel processors now and the AMD processors is really complicated. It really is. There's just a out of order execution and all this stuff. And the RISC guys, they don't want to do that. So I think that's why the RISC systems kind of went away, is that they couldn't offer the price performance that the Intel systems could. They couldn't provide the compatibility through the line. I mean, we had all these software emulators running, and one of the things that we're doing now in Itanium, and actually Alpha started this too, is binary recompilation, where you take a binary, you take an x86 binary, you run it through a binary recompilation, produce another binary, which runs under a special emulation system that mostly executes at speed of the processor because it's translated everything that it can find from x86 code to alpha code or where the target is, but there's still maybe a few pieces around there. And so you actually run the real binary, and sometimes you have to actually flip into a mode that actually emulates the instructions, but most of the time, so binary recompilation has come a long ways, and we would be a lot better off, but still it's not like you just do the binary recompilation and then you say, okay, you just say, I'll do the recompilation and I'll just put it in the store, right? It'll work then. Well, it doesn't, You have to go and make sure, you have to test and make sure, so it's a doubling of the work. So I think the RISC architectures went away in their popularity because of all those things. Now ARM has taken a hold in phones, and it's taken a hold in some of the mobile devices, but ARM is not anywhere near the performance capability of the x86 stuff, and either from AMD or Intel, and they're trying to get there. They're trying to up their performance, but they've been primarily aimed at power, and you use AMD, or not AMD, you use ARM processors in applications where you don't need a lot of power. Maybe you need a little chip. One of the things that's happened is, Intel and AMD to a certain extent is like, we got 1 billion transistors. We just got to build this chip that's this big. The last one was that size. The next one's got to be that size. Even though we have 4 times as many transistors, we're going to build it the same size, right? Well, the ARM guys actually haven't done that. ARM guys have a portfolio of a lot of different size chips. So if you're building a watch, you can build it with a chip that's smaller, right? Yeah. So, but Intel and AMD have never taken this thing about, well, now can build the same functionality in 1/4 the size. Maybe that would be a good product.
Well, this whole semiconductor process technology, the end game with the P4 is we get to maybe 4 gigahertz, and the chip is incandescent. So now we go to multi-cores. So this is a big event in the operating system world that we're going to have 4 processors to play with. How did that start coming into the
Well, we started, NT from day one we built NT to be MP. And our initial RISC prototype, or our reference was MP. So we were MP from day one. So cores are no different than, there's 2 kinds of cores, actually. You think about cores as being autonomous cores or multi-threaded cores. If they're multi-threaded cores, then they're a set of context that's a thread, and the core hardware that actually executes that context. And then you switch among these contexts. And Intel did, it's called SMT, multi-threading, just call it multi-threading. Intel did this early on, but we already had MP support. So the only thing that was kind of a curveball there was that SMP increased your parallelism, but not necessarily your performance. Because you basically have the same amount of execution capability that you had before. You just have multiple contexts that you can run against that. Now, the place that you could gain is that there's delays, like cache misses, where you can say, well, that cache miss, I missed in the cache on this set of contexts, I can switch to another context, and it can immediately execute. Maybe it had a cache miss before, and now that data's there. So you can get, maybe 15%. You can also lose 5% or 10%. So it's very unpredictable. So that kind of threw us a curveball. AMD went the other way, and they did what they called CMT. Multi-threading was called SMT, symmetric multi-threading, and the other one was called CMT, and CMT was chip multiprocessing, which actually put more than one processor on a chip. So the original AMD 64-bit chips were 2-processor chips. So they had 2-row processors. Now, since then, they've all migrated to this multi-core thing where they actually have core logic that shares some other piece. They may share, like you may have a couple cores that share an L2 cache, for instance, which then all the 2 pairs share an L3 cache. And all of that now is all in NT. How many levels of cache do you have? What are they? How many ways set associative are they? And all of this stuff. So the thing didn't really affect NT particularly, but it affected the applications, because the applications now could get more performance if they're multi-threaded. So if somebody started out originally with NT and said, I just have a single-threaded app, then these other processors, they progress through to the point where we're at 3.5 gigahertz, and they're all ready for the next leap to 4, and the next leap to 4 doesn't happen because we can't build it at 4 because we would have such high current leakage that, you're right, it would glow, the thing would glow. So we start building cores, and then it seems to be like a race of how many cores we can get on a single die. I don't know what the biggest one is, but it's big. It's like, I don't know, maybe 80 or something like that. So there's a lot of cores. But for NT itself, that doesn't mean much at all.
Yeah.
Not at all. It's mainly the applications.
Where do we go from here?
So we're in the kind of chronology here. We're at Vista, and we retargeted Longhorn to one code base. So we're actually back to one code base, and I'm still an individual contributor. And I worked on Vista. I did some things for Vista, mainly x64 related, because I've been the guy that was the spearhead for x64. And of course, I say there are 4 of us that that basically did this. We did a lot of it. We did the lion's share of it, but there was a whole nother effort going on in the compiler world where we had a couple of guys from the compiler group that were just absolutely superb, and they did a great job with the compiler. So there was a whole another group of people. I mean, I don't know how many people actually you would say, were responsible for the x64 system, but it was pretty small, maybe 100 people. Mm-hmm. Anyway, so Vista, we shipped Vista. And Vista's a big dilemma because it's like, should we ship it or should we start over? It doesn't look very good. It doesn't look the same as Windows. It doesn't look the same as XP. It doesn't look like the same as anything we've done before. It's different. So we shipped it. And with not very good market reception. Vista was probably the poorest received version of all of the Windows systems that have shipped.
Well, there was some other Bob and some other things.
Well, Windows systems.
Yeah, Windows
Bob. Yeah, Bob lasted, I don't know, 3 to 6 months. That was about it. So Vista shipped in November of 2006. And so I sort of stuck around on the operating system group for a while, but then later on in that year, and I think it was around October, cloud computing was becoming a hot topic. And cloud computing is basically moving back the other way where, we had time sharing systems one time, then we moved to servers, then we moved to personal computers, and now we're moving back to central storage again, where in central computing, where we have a big server farm somewhere that you can interface through from whatever your device is, and all the heavy computing or the heavy storage will occur on that end. And we had server farms in several places, but they were specifically for servers for this or servers for that or whatever. So there was a project or incubation project actually was started called Azure, and it was to produce a system that would provide a platform for people to rent, where they could rent compute power, they could rent storage. And so we decided it was going to be a virtualized system because you want to run multiple instances of operating systems, so it had to be virtualized. And this was at a time when the first virtualization extensions had come out for AMD and for Intel, and were not quite at the level that we thought that we had to have. Specifically, the paging was a real problem, and the virtualization systems that existed, the virtualization implementations that existed at that time were their hypervisors that mainly did shadow page tables. And we thought that direct translation was better, so we decided that we would go with direct translation, which adds more translation levels, but it's direct and you don't have this duplicate copy of page tables on the side. And AMD was the first company that was producing those. Intel came along later, and we decided that our hypervisor would be based on that, and I became responsible for the hypervisor for Azure. And we brought Azure up, and we started a server farm in Quincy, Washington. I don't remember how many servers we had, but it was quite a few tens of millions of dollars worth of servers, which was just our test system, right? And we carried on for about 2 years, and our main differentiation at that point was, and what we were actually asked to do was produce a system that was a platform as a service, which included all the things that you have to do if you have a server. You have problems with configuration control. where you have to keep track of the operating system you're running, what version it is, what versions of all the apps are and all that. And then if you have multiple of these, you have to update them all together. So we built all the infrastructure to do all that stuff, thinking that that was going to be the big thing that people really wanted. And to a certain extent it is, because you don't want to have, you don't want to do this manually. You don't want to manually say, oh, geez, I got 150, I got 2,000. I got 10,000 servers, and a new update came out for the operating system. Well, I've got to update every single one of those, right? Do I want to sit there and do that? Well, no. And there were some internal people in Microsoft that actually had developed some tools to do that, and they were mainly the ones that were running our web services. So we decided to produce another set of tools, and I guess about, I think about 2.5 years into the project, we were doing well enough that Steve Ballmer decided that, well, geez, we ought to really make this a product now. So we made Azure a product, and I forget exactly when the first, I think 2010 was when we introduced Azure with the platform as a service. And at that point, we were out of the incubation, and you know, we're worried about, you have multiple data centers because you want triple redundant logic on all of the storage, and of course we want to do this internationally, so we have, you know, we're building data centers in Germany or in Europe. We're building data centers in the East, in the Far East, and then you have problems about we can't migrate any, you can't replicate any data across geopolitical regions.
Costs money to move it to Canada.
Well, it's mainly because of the geopolitical problems of,
interesting.
you know, if you're storing a replication of data from Germany that belongs to the German government, they really don't want it stored on servers in Texas, right? So we shipped the first version of Azure, and there was a change in the management in the server group, and the guy that would run the server group took over Azure. And at that time, a couple of us decided that we'd go work on the Xbox. And the irony of working on the Xbox is I once sent Steve Ballmer a piece of mail that said, Steve, I got an idea. Why don't we take that $1 million a week that we're losing on Xbox and take it out in the parking lot on Friday night and have a bonfire and roast hot dogs and marshmallows. We can take the people that were working on that and put them on things that'll really produce some good stuff, and we'll save all that money. Of course, it was just kind of a tongue-in-cheek thing. So here I am, like 7 years later.
Going over to the dark side, huh?
Some years later, I'm over on the dark side. So the Xbox was kind of a real new thing for me, because this is working on something where the security is something that's much different than the security for anything else. You think of security, the way you generally think about it is physical. You physically have the machine, it's yours, it's secure, and now you just worry about keeping all those other people out that could invade it through the web or whatever. The Xbox is entirely different than that. We want to guard against people that have a soldering iron and a logic analyzer. They can't break the system. If they do something to modify the system, it will immediately see that it's been modified, and it will do what it's called bricking. It will brick itself. It now becomes a brick. It's no longer an Xbox, it's a brick. So building such a system is kind of interesting, and it requires a lot of detail and attention to security, a lot of hardware, not necessarily in terms of cost, but a lot of hardware, a lot of encryption. AMD is in the business of building custom SoCs. and they built the custom SoC for this, and it has 8 cores, and they're split into 4 2-core groups. But it also has a ARM security processor. So the secure boot is actually secure. You can't decide that you're going to solder some parts on. You can't decide you'll take some parts off and reprogram them and put them back. It will discover this. Everything is encrypted. It runs with a hypervisor, so there's a hypervisor level of protection in the system. It's a 3-headed operating system where it actually runs 3 virtual machines. One is called the host system, which communicates with the hypervisor and is part of the trusted computer base. And the hypervisor, actually, you could think of that as it's running on the bare hardware, but under the auspices of the security processor. The security processor has the capability to just gate off certain pieces of hardware so you can't even see them. So if the hardware is only going to be accessible by the security processor, it has the ability to do that. It has the ability to just stop the processor. It has a lot of control over what's going on.
So back up a bit and say why.
Okay, so the question that we were discussing was why all this security on the Xbox and make it so that it's so the owner can't steal? And the answer is piracy. The Xbox games are called AAA rated games. And AAA rated games means that they're very responsive, they're high frame rate games. Typically, the people that produce them spend a lot of money producing them, and they're not like a PC game where typically in a PC game there's piracy, but they get a big surge when they put them out, and I guess that they figure that offsets whatever piracy that. But a AAA rated game is one that's a high expense. It might be $100, and we guarantee that people can't pirate those games, and we actually get money for that. So if they can't pirate games, and we can convince the people that write the games they can't pirate the games, we make money because of that.
Okay. So you're talking about all the security functions, and so you worked on the hypervisor.
I work on the hypervisor, and the hypervisor isolates all the memory, does all the scheduling. One of the things on the Xbox is that, generally an operating system you want to share. On the Xbox, you don't necessarily always want to share. And there's a lot of actual physical partitioning of the system, depending on what you're doing. If you're running a AAA rated games, we'll take a set of cores and dedicate those to the game in a VM. And so they don't deal now with the interference that they get with other things going on in the operating system. And there's a lot of housekeeping stuff that goes on. And the other things that go on Xbox is you actually can be running a game and viewing live TV at the same time, or even Skyping at the same time, or running the Internet Explorer. So, and not having them interfere with each other. So if you're running a game and it's in the foreground, you got 6 cores dedicated to you. If you're running a game and it's in the quote background, in other words, you're focusing more on watching TV, then you have 4 cores, and the other environment has 4 cores. So we have 8 cores total. So we're constantly switching these cores around, and the hypervisor is doing all that at the command of the host system. The host system's keeping track of what's going on. So it's a much different. You think of this as like you think of virtualization as you're running multiple operating systems. Well, you could think of the Xbox as just virtualization, but it's really not, because all this is the operating system, which we call Hydra. Mm-hmm. And it really has these 3 different OSs running, or 3 different VMs running, all right? And one of them, the system OS is our shared resource environment, where you actually could be running things that were like, you'd be running live TV or Netflix or Hulu or whatever there, and it has all the UI. So everything you do with your game controller is interfacing with something in that particular operating system. But all the device drivers and everything are in the host OS. So there's some communication between the two through shared buffers. And the game is setting it in here in another VM, all right, with its own resources and whatever. And so the memory is separate. It's not like a demand page system where, like a time sharing system where you steal pages from Joe to give to Sally, right? They get what they get so that every time that game runs, it runs the same. The audio doesn't glitch, the video doesn't glitch. And of course, behind this is some pretty good GPU hardware.
Mm-hmm. So this has got you fully engaged in terms of the future of Xbox, or you have your eye on something else?
Right now, I don't have my eye on anything else. I'm sort of just trying to keep up with what we're planning to do in the future, which will be, I mean, most I can say about that this time is it's evolutionary. There are some thoughts about, what do we do? Should we really have a console, or should we really try to beef up the PC environment to be able to run these AAA rated games? And what would that mean? It's not going to be as secure. For instance, on Xbox, there's a bunch of certificates that you get when you buy one, and that say their certificates say what you can do. Well, if you're a consumer, you get an Xbox that you can play games on, and you can do these other things that what are their apps for. You can't run kernel debuggers, you can't do any of that stuff. So there's no opportunity for people to run those kind of attacks. But on the PC operating system, that you can't rule that out, because somebody buys a PC, they say, I own the PC, it's mine. Now, thankfully, from the day we introduced Xbox until now, the people that buy Xboxes, they actually have become accustomed to the fact that that environment doesn't really belong to them to tinker with. They can't load device drivers. They can't put code in the operating system. The typical attacks that somebody would have through the Internet Explorer or the browser are not possible, or they're severely mitigated by the way the layering in the system. One of the things that the hypervisor does is, we do all this through, I won't call it cryptography, but it's secure hashing, is we use nested paging, which means that the hypervisor has the real page table and the real access bits. And the VM has what it thinks are the page tables and what it thinks the access bits are. But it can't get an execute bit turned on unless the hypervisor turned it on. The hypervisor will only turn it on if it's in a page that has a hash that we recognize. So you can't inject code in the operating system. If you find a buffer overflow, then the best you can do is maybe you can jump somewhere where you can find a gadget, and a gadget is a bunch of bytes that are executable but not necessarily on instruction boundaries, that do some weird thing. Since the x86 is a variable length instruction machine, there's no nice crisp instruction boundaries, so you can jump into the middle of instructions. So that's typically what these guys do, is they find a buffer overflow, they jump into the middle of one of these gadgets, which then jumps somewhere else into code that they've loaded or something. But you can't do that on the Xbox.
So let's shift gears into little prognostications about the future. What's the future of operating systems?
That's a good question. Well, the question is, what's the future of operating systems? And VMS is still alive after whatever it's 35 years, a little over 35 years.
Yeah,
it's
37.
37 years. VMS, I do not believe, is nearly as big as Windows is. Windows, I hate to guess how many lines of code are in Windows, but I think it's well over 1 billion. It might be several billion. It's huge. Linux is smaller. Unix is sort of gone. I really thought that Linux would go the same way that Unix went, where everybody took Unix, got a license to it, and then tried to add their value by making it incompatible with all the other versions of Unix, which was great for us because it just made it so that there was fragmentation. Linux seems to have not gone that way. I mean, they've pretty much seem to have held themselves to be compatible. But still, that's a huge system too. It's not as huge as Windows because it doesn't have 28 years behind it yet. You know, it's got 15 or whatever it's got. But in 10 more years, it'll have that too. There's a lot of little things that you can do, like there's people that are building little operating systems for engine control or something, but to build a big operating system is to build some level of compatibility to run all these apps that exist is a very large effort. It may be an effort that even the US government wouldn't want to take on. So the thought that there's going to be a new operating system at the level of Linux or of even Unix or even NT is kind of like, you know, it's going to be difficult. Mm-hmm. I don't think it's going to happen if that happens, it's going to be a long time from now. And it'll happen, if it happens, it'll happen because the complexity of the code bases grow to the point where it's like, do we want to solve the complexities of the code base or do you just want to throw it away and start over? And people may say, well, we just want to throw away and start over. Yeah. However, throwing it away and starting over doesn't mean that you can just junk the compatibility, because you can't. You can't junk the compatibility.
Is big data kind of a fork in the road for what an operating system is?
No, big data, the way I understand big data is just, it's employing applications to visualize, analyze, sort through big sets of data to find relationships that you otherwise couldn't find. Okay. It's not really an operating system per se issue. It's more of a data analysis thing, and it's, you know, we have these huge data sets. We were doing this stuff at DuPont. We were doing one of the things they did at DuPont. They did their own program called Rammer, and Rammer stood for regression analysis and multiple regression or something, mm-hmm. which was basically, you're all the time at these chemical plants, you're trying to take the data that you collect and see what environmental variables, human variables, operational variables, chemical purity and whatever, what correlates with what, so you can rise to the optimum on some curve.
Some process.
Some process, right? And so that's part of the engineering services department was a math and stat group that did just that, right? So we've been doing this stuff, but now people are starting to look at it in terms of things like marketing, you know, where do you target ads, and a lot of different things. And I don't think it's per se an operating system thing. I mean, at some point we may have, in fact, we probably already do have big cloud applications that you can buy and run and provide your data.
And have thousands of processors running on.
Yeah, well, one of the things that's nice about the cloud is the elasticity. Is you can say, I only want one processor right now or one core, or you could say I want 10,000. And you could get 10,000 processors all running in parallel. And maybe they would be running as multiple instances of VMs, or they could be running as multiprocessing within a VM, right? So,
is there any hope for the general decomposition of programs into parallel processing?
Well, you know, people keep banging away at that stuff, and it keeps getting better. People have been doing that. You know, Ken Kennedy at RISC. I mean, you maybe know Ken Kennedy was the big guy for the Dusty Deck Fortran. and infamous. And I'm sure he must be a fellow. Is he not a fellow?
I don't know. Yeah.
He was part of the Terra Cray startup. He was doing Dusty Deck Fortran in 1970, right? Where they're taking Fortran and trying to take Dusty Deck Fortran and compile it so it could be vectorized and done in parallel. And there's just lots of stuff going on. I think more of the stuff is going on now to not necessarily take the old stuff and make it run in parallel, but to always produce the new stuff to run in parallel. One of the things in Windows 10, in fact, I think it was in Windows 8 too, is user mode scheduling, to make it so that you can have tens of thousands of threads and you schedule them yourself so that there's a minimum overhead because you know how you're switching. You don't necessarily have 10,000 processors. You might only have 20 processors, but you have 10,000 things that you might schedule. So there's sort of a move in a direction that's partly what was driving that was the core frequency thing, where people realized, I don't know when, that was about 5 years ago or so, we realized that when in fact Intel said within 10 years we're going to have a 10 gigahertz processor, and then they said, oops, we're not probably ever going to have a 10 gigahertz processor because of this problem, unless we find some other way to build transistors. So being able to run multiple threads and schedule them yourself became something that at least our people thought was essential to being able to exploit parallelism inherently in programs from the start, rather than saying, oh, we're going to take this old program and make it run in parallel.
What do you think of AI, current state of AI?
Well, AI is doing some things now that I think, when AI started, there was this huge uproar about, oh, well, geez, it's not going to be long because computers going to be doing everything. And it wasn't long before we thought, well, will computers ever do anything? But now, there's a lot of AI that's going on that's pretty groundbreaking. Like, well, I'll call this AI. I don't know you call it AI, but I think the Skype translator is absolutely unbelievably something that is just unbelievable. This is where, I don't know if you know about this or not, this is where you can be French and I can be Spanish, and we can actually talk to each other, and the Skype will automatically translate it. When I talk, trans my language to your language. That's unbelievable. That's unbelievable.
Right. How many PhD theses were written about this before it happened, right?
A lot. And now we have, on Windows we have fingerprint recognition for logon, and Debbie's like, she just got a new phone. She dropped her phone, I guess yesterday morning, and broke it. And she says, she's got her new phone, it's got Windows 10 on it. And she says, look at this. I can log on with my eye print, my iris print can log on. So I think AI has really taken off. The other thing, I guess, AI, I guess you should think about computer-controlled cars is AI. And, I think that's great, but I see on one of these things that you gave me, there was a question about, will you ever sit in the back seat of an AI car? And I think the answer to that is not for a long time. And I tell you why I believe that. I believe that because that kind of AI is a little different than the speech thing. It's like the difference between having a machine like a CAT scan machine kind of machine where you have a real-time control of that machine, and if that control goes wacky, it kills somebody, as opposed to we're speaking back and forth and we garble a word. That's a very different thing, right? So knowing how big and how complicated Windows is and how complicated and big Linux is, I think that there's a high probability that there is a large number of bugs in the software, unless it's extremely simple. Now, they may have taken Linux and stripped it down, or whatever they took, and stripped it down to such a small thing that they can actually reasonably be able to prove that it's correct. However, computers are not 100%. They have, every once in a while, there's like, what happened? It just went away. Tandem built systems that were triple redundant logic or whatever. So I don't know. I haven't read anything about whether they have triple redundant controllers in these systems that control cars, but I would expect they do. And the other thing is, what happens when, one time we're in Lancaster, California, and we're going to a racetrack, and we've rented a car from Hertz that has a Neverlost. And guess what? We lost the Neverlost. And we lost it because the atmospheric conditions were such that the GPS could not work. So what happens when you're whizzing down the highway and those atmospheric conditions occur and the GPS no longer works, your proximity things work, but you don't know where you're going anymore. So I think there's some questions that need a lot of answering before we put cars on a highway at 70 miles an hour and say, yeah, here, we'll get in the back seat and watch TV.